Hello everyone, my name is Poojitha and today I am going to give a presentation on singularity functions and complete set of orthogonal functions in signals and systems. In this session, I will explain about two main and important topics in signals and systems. They were singularity functions and closed or complete set of orthogonal functions. In this session, I will explain what singularity functions are, the different types such as unit step, unit impulse, and unit ramp signals, how we can construct signals using them, and finally, a brief look at complete set of orthogonal functions and their importance. Let's get first. What do you mean by singularity functions? Singularity functions are special mathematical tools that help us model the sudden, discontinuous, or instantaneous changes in a signal. Whenever we have abrupt events such as an switch turning on or off, a short impulsive force being applied, or a signal suddenly ramping up, we can represent these events using singularity functions. They make system analysis much easier, especially when using mathematical tools like transforms. In this presentation, we will first understand the different singularity functions one by one. The first and most common singularity function is the unit step function. It is denoted as u of t. The unit step function is 0 for all negative values of time and 1 for all positive values of time. Mathematically, we can write u of t as u of t equals to 0 for t less than 0 and u of t equals to 1 for t greater than or equals to 0. Graphically, this looks like a horizontal line at 0 until time t equals to 0 and then it jumps to 1 and stays there. You can observe the graphical representation here. This function is very useful for modeling situations where something turns on at a particular time, like applying a voltage to a circuit at t equals to 0. The next function is the unit impulse function. The unit impulse function is denoted as del of t. It is also called as delta of t. It is a very interesting function. It is 0 everywhere except at t equals to 0, where its value is considered to be infinitely large, but in such a way that the total area under the curve is 1. You can observe the graphical representation of delta of t here. You can think of it as a very sharp spike at t equals to 0. Mathematically, the integral of del of t over all time is equal to 1. The impulse function is used to model events that occur in an instant, like a hammer striking a surface or a sudden shock to a system. It is also widely used in finding the impulse response of systems, which helps us fully characterize how a system behaves. Here, the third singularity function is the unit ramp function. It is denoted as R of t. The ramp function starts at 0 and increases linearly with time for t greater than or equals to 0. Mathematically, R of t can be said as R of t equals to t for t greater than or equals to 0 and R of t equals to 0 for t less than 0. It is included under singularity functions not because it is discontinuous, but because it is obtained by integrating the unit step function. On integrating the unit step function, we get the ramp function. The ramp function models situations where an input increases steadily, like a voltage that linearly raises over time instead of suddenly jumping. Now let us see the relation between these functions. This is a very important relationship among these three functions: step, impulse, and ramp, through differentiation and integration. If you differentiate the ramp function, you get the step function. If you differentiate the step function, you get the impulse function. Similarly, on integrating the impulse function gives you the step function, and integrating the step function gives you the ramp function. This relationship is very useful for constructing complex signals mathematically by combining and differentiating or integrating these basic building blocks. These singularity functions are discontinuous functions, or their derivatives are discontinuous. Now let us see the applications. That means where we use them. Singularity functions have many applications. In the circuit analysis, we use step and impulse functions to model switching actions and transient responses. Using Laplace transforms, these functions make the math much simpler and allow us to solve for currents and voltages easily. By this we can solve easily the math problems. In system response modeling, step and impulse units are used because they are helpful to find out the important characteristics like stability, damping, and time response. In real world systems, electrical, mechanical, and even physical, we often need to represent sudden events like voltage spikes, mechanical impacts, or force applications. With the help of the singularity functions, we can all see the important things like voltage spikes, mechanical impacts. Singularity functions make it possible to stimulate such events mathematically and predict system behavior accurately. Moving on to the second part of this presentation, the concept of a complete set of orthogonal functions. In signals and systems, we often represent complex signals as a combination of simpler basic functions. Here, if we express our x of t as a linear combination of some functions like g1 of t, g2 of t, and so on gn of t, it can be expressed as follows: x of t equals to c1 g1 of t plus c2 g2 of t plus and so on cn gn of t. Here, C1, C2, Cn are constants called coefficients. Next, a set of function is called a orthogonal if the inner product of any two different functions is in the set is 0. That means here you can observe integral t1 to t2 gm of t into gn of t dt is equal to 0 when m is not equals to n. That means functions are independent. Here and if m equals to n, it is not equals to 0 because the function has infinite energy. Also, there is another simple condition. The integral acts like a dot product if result is 0. That means functions are or any function x of t in the interval can be expressed as a linear combination of those basic functions. Mathematically, we can write there should be no non-zero function, that is h of t, that is orthogonal to all of the gk of t. Mathematically, that means the integral from t1 to t2 of h of t into gk of t dt must not be 0 for every k except when h of t itself is 0. This property allows us to represent signals uniquely and efficiently. Famous examples of orthogonal functions include Fourier series, where sine and cosine functions form a complete set. This means that any periodic signal can be expressed as a sum of sines and cosines with different sequences. Thank you. That concludes my presentation.